A request reaches your AI feature, and it passes every guardrail. The input is accepted. The output stays within the boundaries you defined. As far as the model is concerned, everything looks completely normal. But there's still one critical question the guardrail never answered. Who sent this request, and were they actually allowed to make it? That's the category error at the heart of this video. We're asking a control designed to govern a model interaction to establish trust somewhere else in the application. A request passing a guardrail doesn't, on its own, establish identity. It doesn't grant permission. And it doesn't verify that the operation belongs to this particular user. Now, that doesn't make guardrails useless. Far from it. It means their position in the system matters. AI applications need layered guardrails alongside conventional authentication, authorization, access control, and software security measures. Every layer has a different job to perform, and when one layer gets treated as a substitute for the others, requests can reach parts of the system that were never truly verified in the first place. Let's start by separating two distinct security jobs. The first job is governing the interaction with the model. This is where guardrails belong. They constrain what can enter or leave that interaction based on the boundaries established for the AI feature. The second job is controlling access to the application itself. Authentication addresses who the user is. Authorization determines what that user is permitted to do. Access control enforces those decisions around specific resources and operations. These concepts work together, but they aren't interchangeable. And a model-facing guardrail can't replace any of them. Picture a request moving through the system. Before the application asks whether the prompt is acceptable, it needs to know which identity is making the request. Before it performs an action, it needs to determine whether that identity has the necessary permission. Then, the access controls need to enforce that decision. Within that verified context, guardrails can constrain the interaction with the model. So the clean architecture isn't guardrails versus conventional security. It's guardrails working alongside conventional security, with each control responsible for the boundary it can actually evaluate. And the trust boundary goes beyond live requests. Developers are also making decisions about prompts, generated code, dependencies, models, and application access. A guardrail wrapped around model input and output can't automatically verify every one of those artifacts. Take AI-generated code. A coding assistant should be treated as a fallible collaborator. The developer is still responsible for validating generated code before adopting it. A suggestion might look entirely plausible and still need to be checked against the project's requirements, architecture, and conventions. Model confidence isn't validation. Fluent syntax isn't validation. Even a clean-looking diff isn't the same as validated software. Dependencies introduce another trust boundary. Every dependency suggested by AI needs to be checked for authenticity and maintenance activity before it enters the project. That review can't be handed off to a prompt guardrail because the decision is about a software artifact entering the application and its supply chain. So there are several verification points throughout the system. The request itself, the user's permitted action, the model interaction, the generated changes, and any proposed dependencies. If you protect only the prompt, the rest of that path remains unverified. At this point, the answer isn't to remove guardrails. It's to give them a precise role. Guardrails are one verification layer within a much larger system. They govern model interactions, while other controls establish identity, permissions, trusted software behavior, and production readiness. Think of the application as a sequence of checkpoints. Authentication verifies the identity connected to the request. Authorization decides whether that identity may perform the requested operation. Access control enforces the decision. Guardrails constrain the model interaction. Then software security measures evaluate the code and dependencies that will become part of the application. For AI-generated code, automated tests and static analysis provide the first verification layer. And the words first layer matter here. These checks begin the validation process. They don't transfer responsibility away from the developer. The assistant is still a fallible collaborator, and adopting the change is still a developer decision. Once you see the system this way, the apparent conflict disappears. Guardrails are valuable precisely because they answer a focused question. Trouble starts only when that answer gets treated as proof of identity, permission, or the integrity of the software as a whole. Now let's turn that architecture into an actual development workflow. Start before generation by giving the assistant repository documentation, trusted sources, and good examples. That context helps AI-generated changes reflect the project's architecture and conventions. It doesn't prove the result is correct, but it gives the assistant better boundaries for producing a change that's relevant to the project. Once the code has been generated, apply automated tests and static analysis as the first verification layer. Tests can check the expected behavior represented by the test suite. Static analysis can evaluate the generated code using the project's configured analysis process. But the verified finding is intentionally narrow. These checks are the first layer, not a complete guarantee. The developer then remains accountable for deciding whether the change should be adopted. Review it as work produced by a fallible collaborator. Compare it against the project's documentation, trusted sources, examples, architecture, and conventions. And if that change introduces a suggested dependency, stop before adding it. Verify the dependency's authenticity and maintenance activity. The pattern stays consistent all the way through. Useful context before generation, automated verification after generation, deliberate developer review before adoption, and dependency verification before expanding the project's software surface. That same production discipline needs to apply to model behavior. Begin by establishing the AI system's performance baseline with a capable model. This baseline gives the team a measured reference point before it starts experimenting with smaller, cheaper alternatives. From there, evaluate those alternatives against the application's real quality and latency requirements. Then select the least expensive model that still satisfies those measured requirements. Cost absolutely belongs in the decision, but it comes after the application defines and measures what acceptable quality and latency actually mean. Prompts need production discipline too. Treat them like production artifacts, version them, and record their relationship to models, metrics, outputs, and experiments. That record ties a result back to the prompt and model configuration that produced it. So, when a prompt changes, a model changes, or an experiment produces a different output, taken together, baselines, measured requirements, and prompt versioning make model decisions more accountable and reproducible. They turn what might otherwise be an informal interaction into an artifact that can be compared, evaluated, and managed alongside the rest of the application. Now we can rebuild the opening request with all of the missing layers restored. First, verify who the user is through authentication. Second, determine what that identity is allowed to do through authorization. Third, enforce that decision using access control around the relevant operation or resource. Only after those checks should the permitted request move forward within its verified context. At the model boundary, use guardrails to constrain the AI interaction. Around software changes, treat the coding assistant as a fallible collaborator. Validate generated code before adopting it, starting with automated tests and static analysis. Give the generation process useful context through repository documentation, trusted sources, and good examples. And before adding suggested dependencies, verify them for authenticity and maintenance activity. At the operational level, establish a performance baseline, measure quality and latency, and choose the least expensive model that still meets those requirements. Version prompts and record how they relate to models, metrics, outputs, and experiments. No single layer can answer every trust question. The complete stack verifies identity, enforces permission, governs the model interaction, and validates the software artifacts entering the application. Here's the practical next step. Take one AI-powered request and audit it from beginning to end. Don't start by asking whether the guardrail passed. Instead, ask what each layer is expected to prove. Where is the user authenticated? Where is authorization decided? Where is that decision enforced through access control? Where do the guardrails constrain the model interaction? If the feature can generate code or recommend a dependency, where are those artifacts verified before adoption? And which software security measures protect the application beyond the prompt itself? If you find one control carrying several unrelated responsibilities, name the layer that's missing. A guardrail shouldn't be asked to establish identity. Authentication shouldn't be mistaken for the authorization decision. Authorization still has to be enforced through access control. And none of those controls, by itself, validates generated code or a suggested dependency. A request can pass every guardrail and still remain untrusted at another boundary. The solution is a clear architecture. Verify who the user is, enforce what they're allowed to do, constrain model interactions with guardrails, and validate every software artifact that enters the application.